and welcome to today's problem. Today we're going to be doing A63 all nodes distance k in a binary tree. So given the root of a binary tree, you want to find the value of a node target and integer k, and you want to return an array of all the values of all nodes that have a distance k from the target node. Okay, this makes sense. We have a couple of examples over here, and just before we get started, I want to take a look at the constraints. Number of the nodes in the trees in the range 1 to 500, okay, unique values, and the target is one of the nodes in the tree. Okay, this makes sense. So just taking a look at this, well, we have the number 5 over here. That's going to be our target, and we want to move for k2, which is why we want to return 7, 4, 1 at the very end, because of 2 away. Now, just after first thought, I guess it's pretty easy to get it for the child nodes here, 7 and 4, but it's pretty difficult to get the 1 node over here. So we have to try to figure out a way which allows you to be able to grab that 1 value. Now I'm guessing like one potential way of doing this is by turning this into a graph, so to speak. And what I mean by that is that we could iterate through the tree, and we can go for every single node. What we're going to do is we're going to associate it, its children and its parent as a path. So let's say like we have like the value 5 over here, which is our target. What we want at the very end is some sort of adjacency list in the form of a hash map. So we'll have like 5 over here, which contains the parent, which is 3, and the children, which is 6 and 2. And then we're going to want to have this for every single thing in the tree. So we have 2, and then we have 7, 4, and 5. 7, 4, 5, and so on and so forth. Now, at the very end of this, what we can do is we can do a breadth first search, and starting from the target node, we can do the breadth first search, and then we can iterate up to k levels. So, for example, for 5, it's k levels to 2, right? K is equal to 2. So we hop out from here. The first level is 6, 2, and 3, and the second level is 7 and 4. So what we can actually go ahead and do is we can move this 1, we can move this 2, we'll grab 7 and 4, and then we'll have 3 and then 1, and we grab 1, and that's going to be our final answer. Now, one thing we also want to keep in mind when we do the breadth first search is because it's a graph, we want to have some sort of visited set, which makes sure that you don't bounce back and forth. So, because like an example of what I mean is you're at 5 over here, and then you have 3, 6, and 2, and 2 has 7, 4, and 5. You'll notice that 5 has 2, and 2 has 5, so we don't want to keep having it bounce back and forth. What we want to do is we want to keep a visited set, which makes sure that you can't have any conflict in terms of he keeps jumping back and forth. If a node isn't visited, then you won't be able to access it, so it'll prevent any cycles. So yeah, that's pretty much my solution. I think I'm gonna go with the just create an adjacency list, which should be at O of 1, because you're gonna have to O of n, because you're gonna have to traverse through every single node in the tree. And then after that, what I'm gonna be doing is a BFS, which in the worst case can be O of n, because you're going to be traversing through, in the worst case, k. And imagine if your k is at the very end, you start off with 3 in here, and it's like a sparse tree. That's going to be O of n in the worst case, and O of n plus O of n reduces down to O of n. That's the big O. So that's, I think, an efficient enough solution. So I'll go ahead and begin implementing that now. So we start off with something like we'll start off with the construction of the adjacency list. So let's start off with the construction of adjacency list. Actually, we'll make a default dict, because we want to initialize it to start off with a list at the very beginning. So from import default dict, and then from here, what we can do is we can have a default dict with a list. And then from here, what we want to do is we want to have a queue to start off with, and then we'll set the queue to be equal to the deck. And then what we want to initialize our deck with is our very root value over here, because that's what we're given. Now from here, while q, if we'll have like a cur equals q dot pop left, and then what's going to happen is if cur dot left exists, then you want the cur, or like the adjacency list, at the current value to be equal to, or to have you want to append it with cur dot left. Likewise, you want to add to the adjacency list, you want to add cur dot left, and then you want to append cur. So you want to have both of them be connected in the adjacency list. Same thing with the cur dot right. So adjacency list cur dot append cur dot right if it exists. Otherwise, adjacency list cur dot right, or yeah, cur dot right dot right. We want to add it to the current one. Yeah, so we'll add this, and then at the very end, what we want to do is we want to add this to the queue. So actually, we'll append this as well. So queue dot append cur dot left, and then from here queue dot append cur dot right, and then that's going to be the finishing, well, like effectively the construction of the adjacency list with all of the items over here. So while the queue exists, yeah, we're gonna do for everything on the left and then everything on the right. Now, after we're done that, what we want to do is we want to actually begin the BFS and return the kth elements, like the k elements. So what we want is we want to have a visited set like we were talking about earlier, and then we also want to have a queue, and this time we want to initialize it with our target value, because we want to do it up to k elements. So for here, while queue, you want to do cur equals queue dot pop left, and then from here, if let's say if k is equal to 0, then you want to return the value. So you want to return, or you want to have that added as part of a result set. So we'll have a result over here, and then we want to you want to return the values of all the nodes. So we want to do res dot append. Yeah, we want to do append the actual value. So we want to do cur dot value, cur dot val, and then from here, otherwise, if this doesn't exist, then what we want to do is you want to check to see if cur, you want to do, yeah, if cur dot left, then you want to do queue dot appends cur dot left, and then if cur dot right, you want to do queue dot appends cur dot right. And actually, wait, I think a better way of doing this would be having a target, a tuple of the target in the current level. So we'll start off with the level equal to, let's say, we started off equal to 0, and then from here, what we can do is we can do a queue dot appends a tuple of the cur dot left, and then the current distance. We can pop this distance, and then we can do distance plus 1 over here. So we'll do plus 1 here, and then we'll do a cur dot right distance plus 1 over here. And then after this, we want to go ahead and return the results as our very final value. One other thing that we also want to do is we want to check out the edge case where the target k is going to be equal to 0, because in that case we don't actually want to do anything. What we want, if k is equal to 0, we just want to return the target itself. So we'll do like if target is equal to 0, or if k is equal to 0, I mean, you just want to return the target.val. So return target dot, actually, yeah, we'll just return the target.val over here. So otherwise, you just iterate through the queue, and then you basically pop from the left. If the element is 0, then you want to append it. Otherwise, if it exists, then you want to add the current to the left and the current to the right. So let's actually do a quick dry run just to verify that our code is working. We'll start off by constructing the adjacency list. Let's say we have like 362, 745, etc., etc. What's gonna happen is you're gonna first initialize the adjacency list, the queue, and then for every single element, what's going to happen is you're gonna be adding to the current elements in the queue. So if there is a current left value, then you connect it and then you append it to the left. And if there is a right value, you connect it and you append it to the right. I think this part looks fine. At the very end, you'll have the adjacency list, and afterwards, what's going to happen is you're going to create a set, and then you're going to set the target with the distance is equal to 0. If k is equal to 0, then you return target val. Oh, yeah. So we actually want to make this if distance is equal to k. So if distance is equal to k, that's when we're going to want to append it to the value. So from here is actually, we want to do it for every single level. So just one thing I can do here for, actually, yeah, I in range length of queue, because we want to do a BFS. for every single value in the queue, that's when you actually want to do it for, that's when you actually want to check to see for everything in the queue thus far, we want to be able to append the, we want to be able to append from the left, check to see if the distance is equal to k, and if the left exists, then we do it, and if the right exists, then we add it. Yeah, so we want to do that. And then for this one, for our queue, if our queue is equal to the root, then if our queue is equal to the root, well, like, because it's a binary tree, we don't need to like do another for loop. We just know there's going to be a left and there's going to be a right, and that's when you're going to actually append it. So for this one, we actually want to initialize the queue because there's going to be more than one element. It's going to be 3 elements, so that's why we want to have like another loop in terms of the length of the queue. So just to quickly verify that this works, I want to quickly run this. Okay, 7 4 when we want 7 4 and 1, and then okay, this makes sense. Let's take a look why this isn't working. Oh, yeah, we actually want to loop through and like check for all the values, not just the current on the left and the current on the right. So maybe instead of this, what we're going to do is for adjacents, or for node in adjacency of the current node, so the cur, what we're going to want to do is we're going to want to do q.append cur or node dot left, and then the distance, or you wanna append the node actually, and distance plus 1. So because it's not a binary tree, you actually just want to add all the adjacents here to the node. So that's what we're gonna want to do for every single node in the adjacency list, and we add it. And then we should move on from here. So if we run this again, adjacency cur should grab the list. Okay. 5 1 5 5. Oh, we forgot to work with the visited thing. So if node not in visited, then we're gonna want to append it to the queue, and then we're gonna do visited dot add the given node. Actually, we wanna be adding the visited whenever we encounter it. So you want to do node or visited dot add cur for here. Okay, yeah, so this way we do what we were talking about yesterday. We make sure, like, not yesterday, we do what we were talking about before. We take a look, and then we check to verify that it's not in the visited before we do it, and then we add all of the children to its all the children to the res, and then once it's equal to k, that's when it's going to be its final results. So if we go ahead and submit this, all test cases passed, and it is like roughly it's pretty efficient, I think, of n plus O of n. Space complexity is also going to be O of n in the worst case, because in the worst case, you're going to be adding everything to the queue if it's sparse, like a tree. And yeah, I think that's it for this video. Thank you guys for watching.